Hey students, how we doing today? What? Oh, not this again. Didn't I do this last time? Didn't I start out with the same bad joke? Can't I think of another one? Not right now. Sorry. But I promise to get a bad joke in this video at some point. Okay, so this is lesson 2 of chapter 6 on experimental design. If you recall, we already covered experiments versus observations, experiment terminology, principles of experimental design, and we started our work here on 3 types of experiments. We talked about completely randomized design. Today we're going to talk about the block design and the matched pair, and then we will do for the next lesson cause and effect, and that'll be the last lesson of the chapter. So not too bad, right? Awful, the worst thing ever. I'm sorry. Yeah, I don't know what to tell you, but life is hard and it gets harder. All right, so we had left off with a completely randomized design. Hang on just a second. I wasn't supposed to work out this way. I needed to hit this button instead. There it is. Okay. So when we had left off, we had talked about having a new drug for drug. I could talk. Having a new drug which supposedly lowers blood pressure. Thank you, blood pressure. And as we had said, we had started off with 40 volunteers, and we had randomly placed half of those volunteers into a treatment group which received the drug, and the other half fell in the second treatment group which got a placebo, which again was a fake pill. And I got another cat coming right at me who's going to go right in front of my screen so I can't see. This is the shy black cat. He's not going to talk. He's not going to talk. Are you? Are you, fat black cat? No, you're not. All right. So we randomly assign half the individuals to one group, half the individuals to another group. And as we had mentioned, it doesn't necessarily have to be half in one group. I could put 25 in one group and 15, or 30 and 10. Of course, the math is gonna be nicer if we get equal size groups, but it's not necessarily a requirement. So let's say out of these volunteers that we had 20 males and 20 females. Well, what are some other factors maybe? Let's think of some factors which might influence blood pressure. What factors might have some effect on this particular experiment? What can you think of? There's a lot when it comes to blood pressure. We already talked about the weather. Let's see, what else could it be? Gender, it could be males and females. They could react differently to a drug. Maybe males or females react stronger to the drug than others. Age. We haven't talked about age. Young people could respond differently than older people, or middle-aged people could respond differently than the elderly. Obesity. Maybe if you're really overweight, it might affect you differently than if you are underweight or at weight. Level of exercise. How healthy are you? This might have some kind of effect on how the drug works. Maybe people who work out more or have more exercise will respond more favorably to a drug. We don't necessarily know. Family history is a big one when it comes to medical problems. Does high blood pressure run in your family, or is it just unique to you? So, well, what's the problem with completely randomized design? It's not the worst, but if you can imagine, in our volunteers we have a mix of all these genders. We have people of different ages. We have people who are overweight and healthy. We have people who work out a lot and people who don't, and we may have people with family history. So when we think of all these major factors that could have an influence on our experiment. Let's just say, for example, as I said here, the downside to a completely randomized a downside to completely randomized design is that we don't have control over what factors end up in each group. As I said, if we did have 20 males and 20 females, by random process, maybe 18 of the females were placed in one group that received the real treatment, and only 2 females received the placebo. So now if you did measure an effect between the two groups, again, this could have happened by random chance. 18 in one group, 18 females out of 20, well, there's a pretty small chance of that happening. But in theory, maybe something more like 15. That has a decent chance of happening, 14 or 15 females in one group. So now all of a sudden, if you do measure a difference between the two groups, who's to say is that difference the effect of the drug, or has the effect of the drug been confounded in let's say, the gender, that males and females respond differently to your drug? So again, let's say there's a significant difference between the groups. How do we know if this difference is not confounded between the effect of the drug and the gender? The best way to account for, especially an experiment like this where there are very many factors that could possibly influence our response, is doing what we call a block design. And in a block design, what's different than a block design is that before we start randomly placing people into groups, we split them up into what we call blocks. And the block would be putting people into groups depending on some level of a factor. For instance, it could be males and females. It could be those who exercise or those who don't. It could be those with family history or not. Any one of those factors we could have started out blocking this experiment by. So again, we start out by blocking. We put individuals into groups, and then within those blocks, then we randomly assign within those blocks who gets the treatment and who doesn't get the treatment. So let's try to do a block design of our blood pressure medicine here that we've come up with. And we want to start with, again, what we think a factor is, or really what might be the most important factor. Would be the best place to start. But when all else fails, it all came up at once. Well, that's okay. When all else fails, we can always use gender, because it wouldn't be unreasonable to assume that males and females respond differently to the drug. So what we would do here is beginning splitting up the 20 males and 20 females. And then within these 20 males, randomly assign half of them to get the drug and the other half to get a placebo. And same thing with the females. Randomly assign half of them to get the drug, and randomly the other half would randomly get the placebo. And I just want to illustrate here, this first step of blocking is not random. We purposely choose here, purposely choose the blocks, like the males and females. That's not random. But then once we get into the blocks, this is where we randomly assign who goes into one group, and then we compare. And what's nice about this comparing is, let's say up here, I compare between the males and the placebo, and I find out maybe there is a significant difference between the drugs. Like, the drug seems to have a good effect on males. But then what could possibly happen is I can look here at the second comparison, and maybe for whatever reason, there's not a significant difference between the effect of the drug in females. So this tells me probably more information than I knew from the beginning if I just did a completely randomized experiment, because now all of a sudden I've seen that, hey, there's a significant difference between how the drug works in males, and maybe there's not a significant difference in the females. I found something that could be of great use for my study. We don't only have to block once, we can block twice, we can block pretty much as many times as we reasonably can. For instance, maybe I started blocking with males and females, and maybe now, again, maybe I thought an important factor was not only gender, but maybe I also feel that an important factor is how healthy are people, what's their level of exercise. So now I can block, I could maybe start out initially blocking between males and females, and then I could look at the males and all those who exercise a lot, I could put them into one block, and all those males who don't exercise, I put in a different block. And same thing here with the females, I block those who exercise a lot and those who don't exercise, whatever that spelling is. And then again, now within this high group, within the males who exercise a lot, I'm going to randomly assign a certain amount to get the drug and another certain amount to get a placebo. And those who don't exercise a lot, I again can assign half of them to get the drug and the other half get the placebo. Same thing here with the females who exercise a lot. Split them in half, half get the drug, half get the placebo. Again, it doesn't necessarily have to be split in half, but especially with 40 volunteers, we want to make sure that there's at least a few people in each group by the time we're done blocking. Now again, when we do these comparisons here, what can we get from these comparisons? Well, now I can not only let's say, again, let's just imagine something. Let's imagine that here I did find a significant difference between the males who exercised a lot. I found that those who took the drug had significantly lower blood pressure than those who took the placebo. But maybe here, for the males who didn't exercise a lot, I did find, or I did not find, a significant difference between those who did or didn't. And maybe between all of these groups, I didn't find a significant difference, except for only I found a significant difference in the males who exercised a lot. That would be very beneficial if I'm studying this drug. So it seems like there's some way that this drug is reacting more positively towards males and males who exercise a lot. And this would be very handy information. If I'm a doctor, if I have a patient with high blood pressure, maybe if I feel like, hey, they're a male and they have good exercise habits, maybe I want to give them this drug. But maybe if they're a female, regardless of their exercise level, I wouldn't want to give them this particular drug. And just to show you here, to kind of break this down a little bit more here, I have these NRs. I abbreviated these NRs for not random. When we split individuals up into groups here, again, we don't randomly select the males, and we don't randomly select exercise or low exercise, because those are already factors. Every individual is going to have their own level of factors. So this is gender. This is one of the factors or blocks. This is exercise level. This is one of the this is one of the factors or blocks. And lastly here, this is the treatment, again, either getting the drug or the placebo. And I put these R's here for this is where the random assignment occurs. Big part of experimental design, randomization, is that every body gets randomly assigned to treatments, to treatment groups, and I'll explain why that's more important when we get to cause and effect. Okay, our last kind of experimental design of the chapter is called matched pair, and this is what occurs when experimental units or subjects receives both treatments. And I'm going to limit it to two here, or else two treatments, or else things are going to get a little crazy. And the order which treatments is assigned is random. So, for example, there it is. For example, the same blood pressure same blood pressure example we've been working on. Maybe if we have individuals, we're going to give each individual the drug and the placebo, and then we're going to compare the blood pressure when it's done. So, for instance, maybe an individual subject, maybe we flip a coin, maybe we have some kind of random process, and we decide that they're going to get the drug first. And maybe in this case, they get the drug for 8 weeks. Maybe there's a cool down period, maybe there's like a 2-week cool down period, and then we give a placebo for 8 weeks. And then we compare, well, what was their blood pressure their first 8 weeks while they got the drug compared to their blood pressure the last 8 weeks when they received a placebo. Now, as I said, randomization is still important in the experiments, and the randomization here in a matched pair is going to come from which treatment they receive first. For instance, maybe we had another subject in our study, and his name is Steve. And Steve randomly got the placebo first, and then for 8 weeks had the 2-week cool-off period, and then got the drug for 8 weeks. Why is that randomization important? Well, in this case, it's important for the reason that we don't want the order the drugs are given in to be a factor by themselves. Maybe for some reason the drug works, I don't know why it would work better the first 8 weeks and then getting a placebo afterwards. But again, maybe it could be something about the weather. Maybe if this experiment was all done at the same time, this way by having random assignment of groups, say about half the subjects could get the... Sorry, there's my cat again. Hey, kitty. Half the subjects could... Oh, both cats. Well, it's a kitty party in here. So, sorry, going back to this. If, for instance, if all subjects got the drugs first and then the placebo second, how do we... And again, let's say there was a significant difference now between the drug, between the blood pressure of those who took the drug versus the blood pressure when those were on the placebo, taking the placebo. How would we know if it wasn't the weather or the order that it was given in? So again, the randomization is going to distribute the lurking variables at least as randomly as we can. So every member of the group has an equally likely chance of either receiving treatment or not. All right, I think that's good for the day. Sound good? You want more? You want more? Too bad I don't have any more ready for you. Sorry to disappoint you. All right, happy studying, ladies and gentlemen. Bye-bye.